Look, there are reactions. Nucleophilic SN2 and SN1. SN2 is when both of them are connected, right? So the nucleophile and the thing which is going to get substituted or which will leave, both are connected at the same time. So there are three things which affect these kind of reactions. This is I'm talking of SN2, not SN1. SN1 is different. So what happens is the three things which are connected are whether if it's a strong nucleophile, then it will be a faster reaction because uh, you can see from the energy level diagram, it will be a faster as the reaction proceeds. This is producing a higher energy, this thing. So it requires more energy, the weak nucleophile. An unstable compound is formed here, but strong, stable. So this supports strong nucleophile. Stronger is lower energy. See, so after the transition state, it forms a lower energy compound, more stable. Similarly, if it's a poor leaving group, then it forms a higher energy. So one, strong nucleophile support, poor leaving group support, and if it is hindered, it is a high energy, so unstable. Unhindered, very stable, so low energy. So it supports. So there are three three things which the effects of which is better for SN2 or SN1. So SN2, if the nucleophile is stronger, I mean, charged are stronger nucleophiles than neutral. So stronger bases are stronger. This supports. In SN1, there's no effect. You know why? Because the rate determining step is the slowest step, and the slowest step is when it breaks down. When this forms a carbocation. So you see this carbocation. The nucleophile is still absent here. It's not there, so it's not relevant. And we know that the rate is dependent on the haloalkane concentration, not the nucleophile. So in this the in SN1 the nucleophile strength is of no relevance. So if you should know that the factors to consider in any nucleophilic substitution are the nature of the nucleophile, the substrate. I mean, what is substrate means what undergoes the haloalkane molecule which undergoes the substitution, and the leaving group. So we have got all these three are relevant: the nucleophile, the substrate, the nature of the substrate, and the leaving group. In SN2, the nucleophilic reactivity is important. The negatively charged are more stronger than the neutral ones. And even you can see from the base strength also, the order of nucleophile depends on their base strength also. So you can just check the base strength. That will give you the idea of which is a stronger nucleophile. The stronger the base, the more reactive is the nucleophile. And in case of the same neutrality, then you consider the electronegativity. This is going too deep. We'll see later. Then the the nature of the leaving group, like the bond strength. So if the bond strength is less, the relative reactivity is higher. So iodine Ci is a big bond, is a big atom, so the bond is weaker. So this is more reactive compared. So this is comes the leaving group. So first was nucleophile nature, then the leaving group, then comes the substrate. So the substrate is more about steric hindrance. Uh, Attack of bromo is much easier than by bromoethane because there are molecules around it, so it's difficult. Alkyl groups around it is hindered, and the attack of halogen is severely hindered. Tertiary is severely, as the number attached to the increases, the reactivity will decrease. In energy terms, crowding up the alkyl group due to this steric hindrance. Uh, so in SN2, the nature more reactive the halogen nucleophile, the more better it will be nucleophilic substitution for in terms of SN2. The weaker the bond, better SN2 chances of SN2 happening, and less hindrance chances of SN2 happening. So SN2 will happen if the nucleophile is strong, if the bond is weak, and if there's less hindrance. So that's why less hindrance in primary. So SN2 is only happening in primary. And so weaker the CX bond, the stronger, but this is common to both. The SN2 also, the CX bond, because the the bond, is the rate determining, it breaks down. The carbocation is formed. So this is both. It supports both SN2 and SN1. If the bond is weaker, it supports both. The nucleophile only SN2, the strength of the nuclei, and SN1 it doesn't. And steric hindrance is more relevant here, and positive inductive effect, the pushing of here the tertiary show greatest, so is and so is react faster than primary, and here the primary show less hindrance, and they react faster than tertiary. So these are the factors, comparison whether something will undergo SN2 or SN1. You see the leaving group, you see in case of SN2 leaving group, you see in both. In case of SN2, you see the steric hindrance. In case of SN1, you see positive effect. That's why tertiary is more, and positive inductive effect. And here it's this nucleophile strength is also important. If the nucleophile is stronger, then SN2 is. As far as the positive inductive effect is this, that they're pushing the positive inductive, they push the electrons and disperse this charge. So if this positive, it will get dispersed because and so it will become less reactive, more stable. And so it's more stable, so it will be ready to, it will be there for some time, and then this can attack. So if it's not, if it's unstable, then it will just be, so it won't exist. So how will so first step is this is the breaking down, and this stability of this is very important. And stability will be more if there are three groups. So tertiaries, and then the nucleophile can come and attack. This is rapid, so it doesn't really, this is not so important, neither the strength nor the concentration. Or whatever is important is this, and this bond breaking down, and whether the positive effect is there. This is SN1.